Okay, what I want to do today is to make sure that that we go over a few of the strategic questions that arise when you're trying to figure out how am I supposed to solve these problems. It's not the case that I can give you sort of an algorithm that will say, all right, follow these procedures and you will always get the problem right. That won't work, but I can give some advice, and this advice is taken incidentally from the reference guide to Chapter 5 in the Logic Cafe. I don't know if you've had, how many of you have actually used those reference guides? Okay, you're offered the opportunity to click on a reference guide at the beginning of the class, and sometimes they give you too much at the beginning, but those are useful once you've completed all the tutorials in any given chapter. It's useful to have this summary because it goes over the main stuff, and at least it's easier for me if I have something material in hand by my side. Help, electronic help is always very useful, but if I could just thumb to a page that has a list of things, that sometimes is the best thing for me. So just so you remember, those reference guides to each chapter can sometimes be very useful, and these bits of strategic counsel that Halpin gives, I'm just kind of repeating here, but I wanted to talk about it a little bit. There are, first of all, a number of different tasks that you're asked to do in the exercises in SD, in the derivations in sentence logic. And they're not different from the sorts of things we started talking about in week 1, turning the basic concepts of logic. We talked about validity and logical truth and logical falsity and inconsistency and all those things. But now we're in a position to prove, not just see in a truth table, not just try to intuit impossibility of premises being true while conclusion is false. We can now prove that certain arguments are valid, or we can prove that certain sentences are logically equivalent, or that one sentence is logically false. And what I want to do today is just to go over explicitly what that means to prove these things. And to start with, let's go to the idea of validity. To show that an argument is valid in sentence logic using the tools that you've now got under your belt, you simply take that argument's premises as the premises of a derivation, you use them as the premises, and derive the conclusion using only the rules of SD. Okay? So that, and then the rules are important. I mean, you have to use them as they are licensed. You have a certain license to use these rules under certain conditions. You can assume anything you want, but you can't discharge an assumption except under certain very clear circumstances. You can discharge any derivation if what you want to show is that the assumption horseshoes implies the last line of your derivation, or any subsequent line. Any line in a subderivation is implied by the assumption. It might be implied even without the assumption if you haven't used the assumption in deriving it. And then the only way to get rid of a negation, or to add a negation, a tilde, is by showing a contradiction. So those are the only ways to legitimately discharge an assumption in SD. But if you've done that, and if by the time you're finished with the proof, you've shown that a particular thing follows from the premises, then you've shown that the argument for that thing using those premises is valid. On logical equivalence, to show in our derivation system that two sentences of SL, P and Q, they can be as complicated as you please, but to show that they're logically equivalent, you need to do two derivations. One, you start with a premise P and derive Q, and then the other one, you start with premise Q and derive P. Okay. For logical truth, to give an SD derivation showing that a sentence in sentence logic is logically true, we've used an example of this before. What you do is you derive P from no premises at all. And similarly, to give a derivation showing the sentence is logically false, you take P as the one and only premise. You're trying to show one sentence, again, no matter how complicated it might be, to show that it's logically false, that it could not possibly be true. If you can succeed in doing that if you demonstrate that it leads to a contradiction. So you try and derive two sentences that are contradictories of one another in your derivation. You take P as the one and only premise, and you deduce both Q and not Q, where Q is any sentence at all in sentence logic. And finally, to show the two sentences, or any set of sentences, could be 17 sentences, but to show that the set sigma of sentences is logically inconsistent, do a derivation taking the members of sigma as premises and derive, once again, a contradiction. You derive both P and not P, where P is any sentence of SL. Now, it doesn't matter that this definition uses P and this definition uses Q for the contradiction. Those are just variables. It doesn't matter what they use. The only reason they use Q in this one is because they'd already used P in the same definition. So you want to show that you have to show that there's a contradiction for some other sentences. It doesn't have to be the same sentence as P. All right? Here we hadn't used P before, so the only reason for not using Q is we don't need it. Once again, to show that the set of sentences is inconsistent, show that they lead to a contradiction. Any contradiction at all. Wait. There is one more. This is the general. I mean, this one summarizes, all of the others in a way, but it says that in general, to show that some sentence is derivable from any set of sentences, to say that they're derivable just means that you can use our rules to derive the derivable sentence from that set. I'll read it with its wording, because I think what I just said might have been confusing. In general, to show that a sentence P is derivable from any set sigma of sentences, simply take the members of sigma as the premises of a derivation, and then derive that sentence P using only the rules of SD. If you've done that, then you showed that that sentence can be derived from that set. All right, now I want to spend a bit of time trying this stuff out. So I'd like you to work on this particular problem, if you would. As usual in the classroom stuff that you're working on, this is supposed to be before you've done it in the cafe. So it shouldn't come as a surprise to you that you don't quite know how to do it, or if it's a little confusing. That's appropriate. What we're trying to do is to work through it in class a little bit so that when you get to the Logic Cafe, it won't be totally unfamiliar. I think some of you have said to me that you've had the experience that well, didn't make much sense in class, but then you went to the cafe and then it all clicked in. I think the opposite would have been the case too. I think the two things work well together. So don't feel too badly if this doesn't seem easy. Okay, try this. I mean, I don't know if this will help, but you got to assume something. I mean, you're trying to prove this, right? You don't get to put anything as a premise, but you certainly can start with an assumption. You have to assume something. Okay, let's. The first part is probably the most transparent. The first step. I'm sure I'm doing this right. Suggest a way of beginning. You have to begin with an assumption. This, by the way, is typical of all problems where you're supposed to demonstrate the logical truth of something. You start from no premises. That's what it says here. And that means since you have to start from somewhere, it has to be from an assumption. There isn't another alternative. So, what assumption should we begin with? I'm sorry? Yeah. Assume. Why? Your goal is to get to an implication, an if-then statement, a horseshoe statement. That is, a statement whose main connective is the horseshoe. That suggests that the rule that you're going to use to get there is going to be horseshoe introduction. Doesn't have to be. There are some situations where that may not be the way you want to go. But that certainly is one obvious possibility. So how do you get there? Well, you assume the antecedent, and you try and show that the consequent follows from it. If you can get that, if you can get down here on a lower line of the subderivation, if you can get this right side, the consequent here, curl k triple bar j, if you can get that on some line, then you're in business. Let me see these rules. Now, strikes me that you can get this in one step or several steps. The thing that you're looking for. The thing you're looking for is the consequent. Now, what is a good next step? How are you going to do that? There's no horseshoe in E. Right.
And then if we are assuming that's true, Keith will argue.
Okay, that's not a legitimate step. Everything has got to be done. Oh, come on, go away. Has got to be done step by step. You can't assume anything. So, one way of going through this would be to break this out into those two, whatever it is implications. Like you wanted to break it out into implications. So you would break this out. You would say 1 EQ, you have to, because that's one of the rules here, J horseshoe curl K ampersand curl K horseshoe J. So that's one way of doing it. I don't think that's going to get us very far either, but we can try that. 1 by EQ. All right, is that the rule? Am I got that right? Yeah. By EQ allows us to go to, J horseshoe curl K. I'm going to write all over this, curl K horseshoe J, so I don't have to write real tiny. Right? Pardon me? That's not quite what you want. You want this, which is quite different. Anybody see a very quick, simple Method. Yep.
You could do one communication
Mm-hmm.
and then not K, triple bar J.
1 CM. Right? That's what you had in mind? Look at the commutation, the CM rule. And then how would you get 6?
1 through 2.
All right, sure.
1 through 2.
1 dash 2.
Horseshoe introduction.
That's all you need. Okay, is that clear? But I want to look at this another way. So let's just try. Once.
To like prove one side equal to the other, then the other equal to the other side. The left equal to the right, and then the right equal to the left.
You could do 2 proofs to show the equivalency. Well, all you're needing, what you want to show is an implication, not an equivalence. What sounds like you were working on is trying to prove an equivalence. Okay, what we're trying to do is to prove an implication. So the right method was, and I'm going to do this again, is to assume J triple bar curl K. I want you to look at a different different application of the rule EQ than the one that Russ was alluding to. Go look at the rule EQ. And if you were going to do it this longer way, I wanted this is at least a little bit fruitful for purposes of understanding just how annoying the logic, not the logic cafe, how annoying formal logic can be. You've got to do every step. Now, if I were going to work it out the longer way, not the very simple commutation method, if I were to work it out the longer way, I would not use the one we're most familiar with in EQ, not the lower one. The lower one is that P equivalent Q is equivalent to P horseshoe Q ampersand Q horseshoe P. I would use the upper one. Not that it doesn't matter. Let's try it Russ's way. I think the upper one is just fine. No, it's not. No, it's not. So 1 EQ. I'm trying to see the whole proof right through. I'm going to say, to say that 2 things are equivalent is to say that either they're both true or they're both false together. Okay, that's exactly what the truth table for equivalence says. So you know that it's either J ampersand curl K or curl J ampersand curl K. And I'm going to leave it like that just because to do a double negation requires a whole nother step. I don't want to waste a step. All right. Now, first thing I'm going to do is to do a commutation on that. Curl K ampersand J. And I can only do one at a time. Curl J ampersand curl K. Okay, then I'm going to do another commutation on that, this time on the right side. Okay. Okay, then I'm in a position to go back and use EQ again, and now I can say curl K triple bar J, which is what I was trying to get, and then finally down here 1 through 5 by horseshoe implication. What I wanted to indicate using this longer way, since it's a good deal. It's very unwieldy, but if you were to choose that route, you need to make sure that you're using each rule only once on a given line. You can't do it twice. You're not allowed to sort of go through and do all the... You can do it in your head that way, but we're trying to establish rigorous rules for proofs. So then if you come back and we want to make this dumb enough so that a computer can do it. I mean, that's the kind of rigor we want. We don't want to be exercising our intuitions, and I'll tell you why in a minute. We don't want to be just exercising our intuitions on these particular steps, because intuitions go awry. Our intuitions, no matter how good they might seem, can lead us into serious trouble. Asterisk. I'll come back to that in a moment, because I think it might bear some scrutiny. But for now, notice that the way I went through this is to use this particular interpretation of EQ, not the one with horseshoes, but with the one with conjunctions, so that I can use commutation. I mean, the reason for that is so that I can use commutation in the next several steps. The horseshoe doesn't allow for easy commutation. I'd have to switch it to a disjunction, and then I can commute. So so I use it this way for ease of derivation. And then from this one, I first switch these guys around by commutation. Then in the next step, I switch these two around by commutation. That puts us in a position to go back to our EQ rule. This is equivalent to that. And it might seem to you like this is all unnecessary labor, but it's necessary in order to have derived on each line successfully what we're looking for. And we don't want to let any kind of mistakes slip in. So, and these examples are always sort of silly, and they're fairly simple. Not only the examples I use here, but frankly, almost always when I choose quiz questions, I'm picking examples that are fairly simple compared to other ones that you might find in the cafe. And so, having picked a simple example here for this particular illustration, it might really seem especially egregious that you can't use commutation, the rule commutation, twice in the same line, but you just can't. Always use one rule in one line, and then you just have to extend the lines down to get to where you want to go. Once, though, we've got the curl K equivalent J, that's what we wanted. We wanted to show that that if we assume this, we can derive that, and that's how that we just draw that out as an implication in line 6, 1-5 horseshoe I. Any questions about that? All right, the asterisk. Is anybody on the web right now? Okay. Could you find out for me fairly quickly, because I want something that's authoritative. I want to know Euclid's 5 axioms, just so you'd be able to read them off to me aloud. What I want to get at is this. I mean, the whole purpose in axiomatization, in particular in math, but it's also part of the purpose of working with logic. The whole purpose of axiomatization is to show that the entire system that you're working in can be derived from a small set of axioms. I mean, that's what it means to say we're axiomatizing some discipline like geometry or something else, or like logic, or like anything else. It means that we've derived them from a small set, hopefully, of first principles. That would mean that we say, all right, then the whole system just rests on these first principles, right? And that sort of tidies it up, it organizes it. That's what the advantage of axiomatization is. And in the case of something like math, it really is desirable if your axioms can be self-evident, or as close to self-evident as possible. And you'd like to, another goal of axiomatization is to try to reduce the number of axioms as much as possible. You'd like a nice, neat, simple, short set of axioms for any system that you want to axiomatize. Now, this was accomplished to a nearly perfect extent. It wasn't perfect entirely, but to a remarkably perfect extent. In the case of geometry, it was accomplished 2,500 years ago by Euclid, who was a student of Aristotle's. 2,500 years ago, 2,500 years ago, he axiomatized geometry. Now, the corrections, just so you know, there were some corrections and improvements that needed to be made, but they weren't figured out until around 1900 by David Hilbert, who re-axiomatized geometry in a slightly more rigorous form. But he didn't need to go very far. Euclid had done marvels 2,500 years ago. And the idea was to try and show how all the theorems of geometry could finally be proven on the basis of a small, simple set of axioms. So let's start off with, what I'm trying to get at is the idea that what seems intuitively obvious might cause us trouble. Okay? And while this isn't going to come up much in the Logic Cafe or in the work that you're doing in this class this quarter, I want to just try, I feel the need to justify the idea that we have to really, really try to be extraordinarily careful and cautious in deciding that, oh, well, I can just do this. It's obvious that it's okay. What is the first of the Euclidean axioms? I mean, the whole point here is to try and establish all of geometry, all of the theorems of geometry on the basis of 5 simple, hopefully obvious, self-evident premises. What's the first one?
A straight line segment can be drawn joining any 2 points.
Okay, so that from any 2 points you can draw a straight line. That's axiom number 1. In a way, that's kind of a definition of a straight line. It's what you could draw between 2 points. Kay, were you wanting to talk about the axioms, or do you have something else that, I mean, tell me. Good. I'll ask you for number 2.
To produce or extend a finite straight line continuously in a straight line.
Okay, so these are formulated in a funny way because of the way that they are introduced. But the second axiom is a straight line can be extended infinitely in any direction. That's the definition of a straight line, and it actually has some assumptions in the background about planes in it. But don't worry about that. Self-evident, you know, it's almost based on the definitions of straight line and definitions of points. If you know what points are, straight lines are the shortest curve, actually, to be very general, that can be drawn between any 2 points. And as for straight lines, they can be extended in any direction infinitely. Third axiom.
To describe a circle with any center, any distance, or radius.
Okay, so that you can draw a circle, pick a point, make that the center of the circle. Circles could be drawn with any radius. What's the other part?
Any center.
Oh, yeah, for any point at all on the plane, but any point at all, you can choose that as the center of the circle, and then you can draw an infinite number of circles with an infinite number of different radii. Okay? That's intuitively obvious, right? Self-evident, given the definitions of point, circle, line, plane, things like that, which have been given antecedently. We're not going through all those definitions, but the definitions, you know them, what a point is, what a line is, what a circle is. These 3 axioms are self-evident, right? How about number 4? Yeah.
All right angles are congruent.
All right angles are congruent, which means that they all have the same shape. No matter how long the triangles are, they're all 90 degrees. They can be fit into one another. If you stacked them all up on top of one another, they would disappear because they would all be the same. The only thing different is, what line, the length of line segments that may be meeting at that 90-degree angle. That's the first 4 axioms. There's only one more that you need to build all of Euclidean geometry. And these 4, remember, so far the 4 are something like, you can draw a straight line between any 2 points. Straight line can be extended infinitely in any direction. You can draw a circle from any point using any radius. 4th one says that all right angles are congruent. Well, they've got to be, don't they? They're all right angles, aren't they? All of this is self-evident. Now, okay, what's the 5th axiom? This will also be self-evident in a way, but what's the 5th axiom?
If a straight line following on 2 straight lines make the interior angles on the same side less than 2 right angles, 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles.
Turns out that's about the simplest way to say the 5th axiom. And the first thing that anybody who's ever seen Euclid's axioms says to themselves is, where's all the self-evidence? Where's the simplicity anyway? And it's not simple, but it's self-evident enough. I'll show you what it means. It comes down to this. Take any line on the plane, any line at all. Take any point that's off that line but still on the same plane. Given those two things, there is one and only one line that can be drawn through that point in that plane parallel to that line. Now that's not what those words sound like. This is just an equivalent way of saying it. But notice I had to take a whole bunch of words to say it, and I had to draw you a little picture. But all it says is you can only draw one line parallel to the given line through any particular point off that line in the plane. One. That any other line through that point, see, this is another way of putting it so you can get the intuitive sense. Any other line through that point in that plane is not going to be parallel to this line, right? It's going to be like that. It's going to be like that. Any line that's parallel to this one has to be the same as the first one that I drew. That's what the fifth axiom says. So here's what I'm going to say. It just seemed to everybody from Euclid onward that this has to be a redundant axiom. It can't be that we need this axiom in addition to those other four to establish the basis for geometry. It must be possible to prove this one on the basis of the other four and therefore eliminate it from our list of axioms. It has to be, because it's so complicated. I mean, the other ones are so simple. A straight line can be drawn between 2 points. You can put any number of circles, just varying the radius through around any particular point as its center. I mean, those are just very simple things to say, simple things to read, simple things to think through. This one, I think it should be obvious to anybody with any kind of geometrical intuitions that it's true, but it may be like many another theorem. Lots of the theorems in geometry are quite straightforward, quite evident, but you don't need them as axioms. The objective of an axiomatic system is to reduce the number of axioms down to a minimum. So, for the fifth axiom, for hundreds and hundreds, even a couple of thousand years, more than 2,000 years, there's lots of mathematicians working in that period in lots of different parts of the world, lots of very, 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 very brilliant people. They devoted a hell of a lot of energy to trying to show that you could actually dispense with this fifth axiom, and the way to show that you could dispense with it is to show that it could be proven, derived from the other four. That you don't need it as a fifth axiom, you can derive it from the other four, therefore it would be a theorem, and you could still make use of it, but you wouldn't have to have it as a separate axiom. And that work took the attention of lots and lots of brilliant mathematicians for a couple of thousand years. Until in the 19th century, they proved that it couldn't be done. They proved that the fifth axiom was necessary. Now, why does this make a difference? Well, for one thing, it opened up a whole new area of mathematics called non-Euclidean geometries. Non-Euclidean geometries are ones that make different assumptions in the fifth axiom. That they say, some of the non-Euclidean geometries say, okay, let's build a system in which more than one straight line can be drawn through any point off that line. Let's say it's 2. Let's say it's an infinite number. These yield, each one of those assumptions yields a different non-Euclidean geometry. And so that was interesting to mathematicians. Aha! Look, we can change the assumptions, change the axioms, and we have entirely interesting different systems. And some of them, by the way, that's the geometry of the surface of a sphere, or the geometry of a hyperbola or other conic figure, All of these are different sorts of geometries where you imagine the plane differently than Euclid does. Now again, all right, so what? It's a big deal for mathematicians maybe, but not for the rest of us. Well, still perhaps not for the rest of us, but one of the things that general relativity suggests, and that's a theory that is almost universally embraced. It's got some questions to answer still, but it's almost universally embraced by physicists as the real description of our real universe. The suggestion of general relativity is that our real universe isn't Euclidean, it's one of the non-Euclidean ones. It's a Lobachevskian geometry. It's a real space. So this assumption that dominated mathematical thinking for 2,000 years, which finally proved to be wrong, the assumption that, oh, well, it's so obvious, we should be able to prove this thing from these other four axioms, it finally proved to be wrong, and it had fairly momentous consequences. Once they discovered that it was mistaken, non-Euclidean geometries were developed, and once non-Euclidean geometries were developed, it left physicists like Einstein free to contemplate them as possible geometries for our real universe, ones that would better accord with experimental and observational data. So that's a reason for wanting to be precise, exact, making sure that every line of your proof is well justified, and that you never, ever, ever in a logic or mathematical proof rely on your clever intuition. We don't want to do this. We would love a system that computers could use, that computers could derive these things, because then we know they're not doing no intuiting. They're not going to say, oh, it's obvious. They have to have a rule. And that's one of the great advantages of computers in the modern era, because we can quickly calculate things that would have taken generations sometimes for other people to calculate. All right, anyway, so that was a long-winded justification of attempting to be precise in one's calculations. What I want to do is, let me go back to the one we were working with before, but without worrying too much about that. I want to just go through some particular strategic suggestions about trying to derive things in sentence logic. The first thing we've emphasized many times before, but the first thing you want to do is to look for the goal. What are you trying to prove? Look at it very carefully. What kind of sentence is it? What is its main connective? That will tell you lots about how you should proceed. If it's an implication, what you want is to show that you want to assume the antecedent and show that the consequent follows from it. If it's got a negation sign in front of it, you might want to assume the opposite of it, namely the thing negated. See what happens if you assume that. Maybe you can show that a contradiction is derived from it. And similarly, if what you want to show isn't a contradiction at all, it's just a statement, it might be very complicated, and so you have some trepidation about assuming anything that's as complicated as that. But these things have a way of breaking down into simpler solutions. So if you see something that needs to be proven and doesn't have a negation sign, well, you might wish, it'd be sort of a last resort, but you might wish to assume the negation of it. See if that leads to a contradiction. Then you'd be entitled, if you can show that, you'd be entitled to remove that tilde, remove the negation, and draw what you've concluded back into the main line of the derivation. Usually you'll be given an ultimate goal, that is the main thing that you're asked to derive, but during the course of a derivation you might establish one thing, but you'll have to do another sub-derivation, and so you might have an intermediate goal that you have to achieve. Always consider that. Once you've made your assumption in the first sub-derivation, see if it would be worth your while to assume something else in a second subderivation in order to get to where you want to go. All of these things that I'm outlining here are in the overview of Chapter 5, if you want to grab that. And then if anything seems obvious to you, and a lot of times we have been working with proofs here on the board and says, oh, well, look, we've got A horseshoe B, and we've got B horseshoe A. You know, it's pretty obvious that what we can do, if it would be useful to us, we can immediately use the rule of equivalence introduction. So, you know, look for stuff that's obvious, if that will clearly help you toward your goal. And then, as we've been saying, using introduction and elimination rules, always consider the introduction rules that are appropriate for the main connective of your goal sentence. Focus attention on the main connective. And again, consider the elimination rules appropriate for the main connectives of any accessible sentences. Which ones are the accessible ones? Well, they're any line that is in a derivation or subderivation that you have not yet discharged, that you have not yet finished, that you have not yet completed, is eligible. It's accessible to you. You can use it. That's why we didn't have to use the R rule, the reiterate rule, in that particular derivation that we were talking about earlier. It's because we have it. It's accessible. It's there in the main derivation. We cannot bring something that's, and I'm going to say this physically, because in the Logic Cafe I can do that. We can't bring something that's farther to the right. Let's say we finish this subderivation, we're back working in here. That stuff's now dead, except the one line that we are allowed to bring back. Whether it's the horseshoe, or whether it's a curl that we've introduced, or whether it's a curl that we've eliminated, that's the only thing. Once we've closed that out, that's it. We can't use any of that stuff that's over off on the anywhere to the right of where we're presently working. But we can use anything that's already in the work to the left. I mean, we'll always be working from top down, so it'll always be something above the line that we're working on, but that means that either was given to us or we've established it already, either in the main derivation or we've established it in the derivation we're working on. So the only thing that's prohibited by the word inaccessible is stuff that's been closed out already. Can't use that stuff. So that's part. The second bullet here says, consider the elimination rules that are appropriate for the main connectives of any accessible sentences you may have already derived. And this includes your assumptions. And once having done that stuff, you just go back and do it again as often as you need to until you reach your conclusion. That's basically the three rules, although there's this advice. And I'm not sure, I mean, this is advice that I'm taking from Halpin in the cafe, and so I'm passing it along to you just because it's something he's communicated. I'm not sure I think about this as rigidly as he does, but he seems to, his advice is, wait, that curl E often is something you should hesitate to use. You should wait to use that to make sure you can't use something else for it. And then in that case, follow these two suggestions. When an accessible line has curl as its main connective, you may have to reiterate that statement within a subderivation to provide a contradiction. And then finally, when all else fails, or when you begin to feel desperate, you may have to just simply assume the negation of your goal, whatever your goal is. That's always something that might work. If you have a goal, no matter how long it could be, put it in brackets, negate it. Assume the negation, see if that gets you out of your trouble. You are now entitled to use within your proofs, once you get to the appropriate place in the tutorial, you're entitled to use De Morgan, for example. There are ways to break into those negated, bracketed sentences. So sometimes if you have, for example, if the thing you're trying to prove is a disjunction, try assuming the negation of the disjunction. One of the nice things about that is, because you've got the negation of a disjunction, that allows you immediately to use De Morgan to get a conjunction, which you can then break up using ampersand elimination. So you can sometimes make big progress if the thing you're trying to prove is a disjunction. by assuming in a subderivation its negation, because it'll break up pretty simple. But think strategically. I mean, these are codes and rules, and they're suggestions, and I think that they're good ones, all 4 of these strategic rules. And in the review, or whatever he calls it, what is it, review? Is that what he calls those, the basic, at the beginning of every tutorial he says, click on this to get the review. But whatever it is, it's a summary of all the stuff, the meat of the stuff that goes on in all the tutorials. I do not advise you to try to use those things as shortcuts unless it's absolutely necessary. You have no time at all. But they are good references to have by your side. Maybe that's what it is, reference. I'm not sure what it's called, reference. All right. But consider that stuff. All of these strategic recommendations are made there. I encourage you to go review them there. But in the end, it's going to have to be your judgment. You have to figure out what's the goal. You have to figure out what's a wise strategy. And these hints can be, rules of thumb that can be helpful, but they won't necessarily solve your problems for you. Okay, let me recommend that as you encounter any difficulties at all, you have not, please feel free to use those discussion areas to communicate your problems to the rest of us. And I hope that you will also, be alert to those notes that people might post and come to people's rescue when you can, or come to people's assistance, or chime in and say, yeah, I can't see that either. I've got the same problem. And I will be reviewing that stuff on a regular basis every day for the most part, and I'll chime in when I see your notes too, if you want to do it there. But that can help you get past some of this stuff as you're working on it, and can certainly help as you review material for next week.